let's move on to forces. Unit 2, forces. In order to really conceptualize forces, you gotta ask yourself one big question. What do you need to apply in order to keep something moving? I stole this from Mr. Lindenberger, but it's a great question. What do you need to apply in order to keep something moving? So pause for a second and think about, what do you need to apply in order to keep something moving? And hopefully you've answered nothing. In this universe, you don't need to apply anything in order to keep something moving. And you might be thinking that, I mean, like at the start, I think maybe you probably answered this correctly, but at the start of the year, you'd definitely be saying, no, you need to apply a force. If I stop pushing my shopping cart, it's gonna come to a rest. If I, when I kick the soccer ball and I'm not touching it anymore, it'll come to rest. So this is the first big thing that we all have to wrap our head around. You don't need anything. When there's no external net force, you don't need anything to keep something moving. You don't need to apply a single Newton of force, and we'll talk about units and all that stuff, but you don't need to apply anything. So, this is the first big thing to really conceptualize. And this is what we call Newton's first law. I remember there was a kid in my class, his name is Drew Malati, he might be watching this, and we were learning about rotational inertia, and he was like, wait, what's regular inertia? Like, he didn't know what this was. This is the idea of inertia. And the reason he didn't know what inertia was is because our teacher doesn't really like saying the word inertia or something, like in Unit 2. So, and we'll get to what all that means. Hopefully you can just at least conceptualize that you don't need to apply anything in order to keep something moving. So let's just build on, let's review some things about forces. There are really two types of forces. Contact forces and, I forgot the other name, but like action at a distance force or something. Yeah, okay, let's talk about that. So, if we have a table and we have our little box, there's going to be a force by gravity on this box, right? And then there's also going to be, so just based off this, right, if this is the only force, the box would be moving downwards. You can tell it'd be accelerating downwards, right? But there's obviously that upward force. Someone just gave me a notification. Hopefully it wasn't important. Let me just check. And it didn't stop recording, so it wasn't important. So we have this normal force. This is an upward force pushing up. If you put your hand on a table and start pushing down, you're going to feel an upward force. And that's just the force by the table. So this is what we call a contact force. What is a contact force? That just means a force that's like a touching force. So it could be like the force, the pushing force by your hands. It could be the tension in a rope. It could be a spring. It could be just any sort of touching contact force. And then Fg is just what we call, and I don't know what the actual term is. I call it like an action at a distance force. I think that's what Newton said or something. Keyword is distance. So force gravity acts over a distance. The electric force acts over a distance. Magnetic force acts over a distance. You do not need to know what electric force and magnetic force are. They're really cool, but you don't have to know them. But the main idea I'm trying to get at is there's only one action at a distance force. That's Fg. No other force is going to, unless we're dealing with magnets, no other force is going to act over, no other force is going to act over a distance. So for example, a very common thing people say is that if I'm this person and this is ice, right? So let's just say mu is equal to 0, there's no friction, and then I give this block a push and then it's moving this way. Some people are saying, oh, the force push is keeping it going. Like there's a force push. There's some sort of force keeping it going. No, there's not. If it's moving at a constant velocity, there's not any sort of push force, right? This person cannot use the Star Wars force to keep this moving, right? There's no other action at a distance force. There's Fg, there's your Fn, but there's no this person can't just apply a force over a distance. So just keeping those things in mind. Why is this thing still moving if nothing's touching it? This this because of this. And let's talk about what this is. Newton's first law. So maybe I'll write them up here. So Newton's first law. It's inertia. So what is inertia? This is my like physics teacher's biggest pet peeve. Like when people don't explain inertia, right? So I gotta explain it right. Inertia is just this. Honestly I don't know how to really describe it like correctly. It's really just this idea that stuff with mass is gonna keep it's gonna keep its constant velocity if there's no force on it. So if you think of like a boulder, like it has mass, and if you give it an initial push and it's accelerating, and then you stop pushing it, it's gonna keep its velocity. Inertia is not like a force. There's no force that's keeping it moving this way. It's just saying that it's not gonna accelerate, right? It's not gonna accelerate without a force. That's really what inertia is about. It's why that you don't need to keep something moving if it's why you don't need to apply anything to keep something moving. Now inertia, right? If you think about a boulder versus a feather, right? Which one has more mass? Obviously the boulder, it has more inertia. What does that mean? That just means if I let's say I start applying an opposing force, and let's say they're equal, which one is going to accelerate more? Well, it's going to be the feather. And then we'll get to like why. Inertia is just saying, or this is why, I'll get to the mathematical Newton's second law. But what inertia is just saying is that more mass means it's harder to accelerate. So I'll write that, harder to accelerate. Okay, now let's expand on this with Newton's second law. Newton's second law is really like I don't know what you call it, I guess an expansion pack to the first law. It's really just saying, it's really just saying inertia, but just mathematically, I guess. The equation is that the acceleration, and I'm writing it this way, acceleration on an object is going to equal the force net on an object over its mass. So let's think about what this is saying. First of all, it's saying that, this law is saying that in order to cause an acceleration, you need a F net. Nothing will just accelerate without a force. You always need a force. So if for sure the boulder is going to keep moving if it's already moving, it's going to keep moving. If it's at rest, I need to apply a force to accelerate it to get it moving to begin with. Now, the over m, right? What does that mean? That's just saying that if you have more mass, for the same force, if you have more mass, you're going to have less acceleration. It's sort of that inverse proportionality. That's why, like, if I apply an equal force to both the boulder and the feather is going to accelerate a lot more because its mass is less. Now, you'll always see this as F net. Like, if I multiply m by both sides, you'll always see this as F net equals ma. This is, like, the more famous version, I guess. But I really, to conceptually understand it, please think of it like this. I remember helping a student, and she was, like, always using this equation, and she was thinking that more mass leads to more F net. She was confusing with Fg, but then when I showed her, like, don't think of it like that, think of it like this, like F net causes A, that just helped her out a bunch. So to conceptually understand it, I think this is better, but then just in math problems, I would just use this. It's up to you in terms of what equation you like to use. Let's hold on Newton's third law. I want to keep talking about like some stuff you're going to see regarding these first laws. Okay, so if I gave you we have a push force here, and then we have friction opposing, and we're going to say it's equal and opposite. Oh, that's a little teaser there. And then we also have Fg and then our Fn. Equal and opposite as well. Think in your head, is this object moving or is it at rest? The answer is we don't really know. All the forces are equal. So let's write our sort of F net equations. The F net in the x direction is going to equal the force push minus force friction, and because they're equal, that means 0 newtons for the net force in the x direction. F net y is very similar, but it's going to be Fn minus Fg. Once again, 0 newtons. Did I say newton meters? I'm thinking of torque. I meant newtons. There's 0 newtons. And that's a unit of force. So what this is telling us is that the net force is 0, therefore the acceleration is 0. But this could technically be moving at like 1,000,000 meters per second, right? The forces are balanced, so there's no acceleration. That just means the velocity is not changing. If the forces are balanced, it could be moving at a constant velocity. Like think about like pushing a shopping cart. Your force that you're pushing is opposing the equal force friction back at you. That's why you're moving at a constant velocity. Equal forces don't mean at rest. Now, if I said like the initial velocity 0, then yeah, you know it's at rest because like the forces are balanced out, and so the velocity won't change. Just keep in mind that you don't necessarily know just based off this picture, right? You could just say it's moving at a constant velocity. If the velocity is 0, well, that's still a constant velocity, so that, that's the most general statement you can make. Now, let's take a look at acceleration. Let's say this force friction was, a little bit smaller. Oh, and I can talk about friction more as well. So, let's say you had to solve for, like, the force friction, right? Well, what you would do is you would take your F net, let's just sort of disregard this. You would take your F net x equals force push minus force friction. Okay, and then we know that F net is always equal to mass times acceleration. So then we can substitute ma into F net equals x. And then if we know the acceleration and we know, this force, we can figure out the force of friction, right? Because we just do ma minus force push is going to equal negative force friction. And then you can like switch out the negatives, and then you get negative ma plus force push, whatever, equals force friction. So force friction is a pretty interesting thing. You can have, so the equation for force friction is going to be equal to, and here, let's do this, force friction, kinetic. And I'll talk about what kinetic means and what static means. Force friction kinetic just means it equals force normal times mu. So this let's unpack this equation. Mu is just sort of how rough the surfaces are. That it's the roughness of the surface. If you have more mu, you're gonna have more force friction for the same Fn. If you have less mu, it's like more slippery. We've dealt with mu a lot. And then force normal, it kind of makes sense that force friction increases, right? Because if your force normal is bigger, it's compressing the ground more, and like there's sort of that more, I guess, compression. I don't know if that's really the right term, but it's pressed down more, so it's going to be harder. The friction is going to be a little bit stronger. What note was I going to make? A lot of people, so this is that was a little door thing. A lot of people think this is the equation. This is what a lot of people will use. Equals mg mu. And they'll say, oh, this is the equation for force friction. This is sometimes, right? Because for sure, in this case, Fn and Fg are equal, so you can substitute it in. But I remember one of the most annoying problems I would used to do is when you would have FBDs like this. Oh, I gotta talk about FBDs too. The most annoying stuff will be like this, when you have an angled force. Theta. Force gravity. Force friction. I remember this would be so annoying because then for force friction, you can't just plug in Fn equal, you can't just plug in Fg, right? Because in reality, the force normal is a little bit bigger. It's bigger than Fg because it also has to balance out the downward force caused by the force push. So if you were solving for Fn, you would have to be like, okay, Fn minus Fg minus Fpy, like the y component, Fpy equals 0. So then you get Fn is equal to Fg plus Fpy, and then you have to substitute this whole thing into there. Don't memorize this, just understand it's Fn in general. That's the general equation. Let's talk about static friction really quickly. So static friction is really interesting. Static friction occurs when you're pushing something, but it's not moving yet. So if I had, let's say this box is initially at rest. I erased a nothing. I'm really sorry about that. I was trying to keep it up there. Let's say it's not at rest, and then I start giving it a little push, but it's not moving yet. Well, that's because there's this force friction. And then I start increasing force push more and more. Well, this force friction will, if it's still not moving, what happened is this force friction actually got bigger. So that kind of doesn't work with our equation though, because our equation is saying that force friction K is equal to Fn times mu, right? Fn didn't change because it's still equal to Fg. I'm not applying any downward force or anything, right? It's still equal. And mu is obviously the same, right? Mu is just like the surface. Why is friction changing its value? Well, this is for force friction kinetic. This is for force friction static. And force friction static is actually less than or equal to force normal times mu, right? So it'll be any sort of strength up until Fn times mu, right? If I start pushing at the max, right, it's just going to be barely able to keep up, and then if I push a little bit harder, it'll start moving because this is sort of the max for static, and then it'll turn to kinetic. So let's actually to sort of show that. Imagine if I was graphing. So I think we did this in pivot or with the force sensor. If I was graphing force friction with force push initially, so when force push is 0, obviously force friction is 0. If I push a little bit, then the force friction is going to go up a little bit, and it's going to go up like this. So as I increase my force, the friction also increases up until a point. And then at one point, it's just sort of going to give up, it's going to start moving, and then the force friction is just kinetic. So that's really how force friction works. It's an adaptive force. Just like force normal and force tension, those forces can change depending on like how hard you're pulling or how hard you're pushing or whatever. That's what we really call adaptive force. So yeah, hopefully this is a concept you've been doing in a lot of problems. Let's talk about FBDs. I think we've kind of done them all year. I think that's a main SCP-4 thing. It's just like understanding like forces are balanced, and also like, you know, drawing components as well. That's probably a good skill to have. Not much to say about FBDs. I know that's not the most confusing thing in the world for a lot of people. I will say, if you're approaching like a forces problem, FBDs help so much. Like just drawing an FBD, like it'll basically give you the entire problem. Let's see how much time we're at, because I've been talking for a while about this stuff. Oh, I'm at 20%. Oh, this is 18 minutes. Okay, this is a long video. I'm going to cover Newton's third law. So this is the biggest, like, sort of, I remember I was confused about this when I was learning physics. Like, this is like the most, I feel like, I don't know, this is a big misconception in general. But if I had I'm a really lanky dude. I'm pretty skinny. If I had if the quarterback for this school, let me sort of draw it. If the quarterback, right, for this for Stevenson, and then we can draw the little shoulder pads, and then me, I don't know what number he is. Let's just say 27. If he's hurtling at me, and then we get in contact, and then he tackles me. Who applies the larger force? Everyone is gonna think, yeah, obviously that was my brother. I don't know why he's like that. Everyone's gonna think it's the football player, right? He's stronger. He can exert a larger force, but really, it's equal and opposite. That is kind of the main thing. So let's actually do this for a tractor, or for tug of war. So let's say it's me, versus who do I want to go against? maybe I don't know, maybe my human geo teacher. So if I'm going in a tug of war, then well, really, if I'm drawing FBDs separately, and let's say we're both sort of like tied, like we're not moving or anything, there's going to be the force pull here, and there's going to be that equal and opposite force pull back, right? So why am I staying still? Like why am I not accelerating this way? Well, I'm not drawing the FN and FGs, but there's going to be, actually, my feet are pushing me back, right? There's like some friction with my feet, and then those are equal, and then there's friction with her feet, those are equal. So if she wants to win, it's not necessarily that she has to pull more, right? Because if she pulls more, then this force is going to increase, but then this force also increases, right? So what she has to do is she has to sort of use her feet here and then pull with a larger friction force to sort of have more friction, so we both accelerate that way. So I remember that was a problem on a quiz that a lot of people got wrong, but just thinking through these kind of problems, and as well as like just stuff of like sort of explaining why does like a fly on a car, why does a fly get squashed, but why does the car sort of just keep moving? Well, if you think about equal and opposite forces, if we have the bug here, the force that he exerts on the car is, so let's draw the FBD for the car, right? I'm not going to draw the other forces, but what I'm showing is that the force the bug exerts, force bug, is equal to the force the car exerts, right? They're equal and opposite. The key is really just Newton's second law. They have the same force, but the bug has way less mass. It's going to get way more acceleration. The car is so much heavier, or not heavier because it has to do with the weight. It's so much more massive. It's going to have way less acceleration. Weight, I haven't even talked about weight. FG is such a thing we've been doing like sort of all year. I forgot to really explain it, but if you do need like a true unit recap, you got to talk about FG. FG is always the force that points down. So if you have ramp problems, I was talking about ramps too, this is such a long unit. If you have a ramp, right, a lot of people want to say, oh, Fn points this way, so Fg points this way, but Fg always points down on Earth, right? Even that's not necessarily true, but in physics, yes, it's always going to point down. And we always just know Fg equals mg, where g is equal to 9.8. But then the more sort of, I don't know if this is unit 3 or unit 2. This might be unit 3, so I might just save it for that. Let's just, yeah, there you go. Fg equals mg. So for questions like this, you would have to split up, right? You have to split up fgx, or fgy, and then fgx. And then you can use geometry to figure out that this angle is equal to this angle. So you can do your trig like that, and that's really how you approach ramp problems. Yeah. I'm trying to think, what else should I explain without wasting time? Which is important to know. Doing ramp problems is really important. Doing FEDs is really important. Doing, I guess like stuff like you solve for acceleration, right? Using FNet. So I say like, oh, I exert a force on my bicycle of 2 newtons, and it's a 10 kilogram bicycle. How far is it going to move in 3 meters? What you would have to do is you would have to solve for acceleration. So you'd have the bicycle is sort of, what I say, 10 kilograms, and I apply 2 Newton force. So you would draw your FPD, you would see 2 Newton force. So A equals 2 newtons over 10. So you have A is equal to 10 kilograms. You would have 1/5 meters per second squared, and then you would use kinematics. You would use that, okay, how much time does it take to go 10 meters, you would do 1/2 AT squared, where V initial is 0, right? It's all cumulative. It's all cumulative. So just understanding that kind of stuff is really, really important. What else? What else is important to know? Newton's third law, important to know. Ramp problems, like just understanding the angles. And you can also have crazy problems like you know, if you have like a chandelier. You have two tension forces and they're equal. Maybe you could find like how much is in each tension and stuff like that. So that's really just the gist of. Oh, actually, one important thing to know is like two-body problems, right? So if you have a two-body problem like this, you know, you can treat it like one system, so that the only net force is going to be Fg on the whole system, and then you could say that the acceleration of the system is going to equal the F net on the system, which is only Fg of block 2, because Ft is external, and we'll just say there's no friction, and over the total mass, so m1 plus m2. And then if you had to find the tension, everything accelerates at the same rate, so everything has the same acceleration. Once you find the acceleration of the system, you can do that. The acceleration of block 2 is going to equal Fg minus Ft over m2, and then using this acceleration, sort of plugging it in, and you can find tension. So if you want to find like internal forces, oh, that's another thing. Internal forces don't cause acceleration. You can't exert a force on yourself. I think we're kind of okay with that idea, but just remembering that if you do want to find an internal force, you have to just break up your system to be like them separately, right? And then just doing it like that. So with that said, I probably am missing stuff. I didn't plan this video out like I did for kinematics, but hopefully this gives you a really good conceptual understanding of Unit 2, and just refreshes your memory on a lot of things. So yeah, thank you for watching. I'll try to get this video out by tonight, if I'm not busy.